the axis of rotation. So, the coefficient of inertia in rotational motion is called moment of inertia. जो ट्रांसलेशनल मोशन च इनर्शिया क्या सी इत्थे कोएफिशिएंट ऑफ इनर्शिया कहने इनू मूवमेंट ऑफ इनर्शिया कहने हैं उत्थे जो ट्रांसलेशनल मोशन च इनर्शिया हुंदा है इट डिपेंड्स ओनली अपॉन मास बट हेयर अलॉन्ग विद मास it depends upon distribution of mass about the axis of rotation. So, moment of inertia plays the same role in rotational motion as that of mass in translatory motion. Also, to bring about a change in the state of rotation, you have to apply torque. So, in the case of rotational motion, what we apply is torque. In the case of translational motion, to change the state of rest or the state of uniform motion, we apply force. This is an example of a tightrope walker. Why he carries a pole in his hands? कोई व्यक्ति अगर रोप दे उपरों दी मूव करना चाहे तो तुसी देखोगे हमेशा उसदे हथ दे विच एक रॉड होया करदी एक पोल होया करदा है. This pole is used to increase his rotational inertia. If he starts to wobble, अगर डिगन लगता है, the pole starts to rotate, but its inertia resists this. So, the tightrope walker has time to adjust balance and not rotate and fall. Better balance means more rotational inertia if pole is longer and has weights at the ends. ज़्यादा रोटेशनल इनर्शिया कदों होगा अगर इस पोल नूं असीं होर लंबा कर दईए और आले दुआले वेट्स हैंग कर दईए. Rotational inertia depends upon axis around which it rotates. Let us take the case of example here of a pencil. It is easy to spin the pencil like this. If you want to spin it at its center, it becomes slightly harder, and if you want to spin it at one end, it becomes more harder. Let me ask you a question. Consider balancing a hammer upright on the tip of your finger. Would it be easier to balance in this position or in this position? Your answer is it is easier to balance on the right. Why? Because it has got more rotational inertia. What about the heavy part here? Heavy part has gone up. It is much farther away from the axis of rotation. So, it gives you more resistance to the rotational change. Similarly, consider the meter sticks that are shown here. One with the clay at the top. If you release them, which one will come faster on the ground? The one without the clay or the one with the clay, or both of these will reach the ground together? Your answer is one without the clay. Why? The one without the clay, because the stick with clay has more moment of inertia. So, resists rotation to ground more. What is center of mass then? It is nothing but the weighted average of the positions. Each position appears in proportion to its mass. It is the sum of products of masses and their position vectors divided by total mass of the body. If the two bodies, if you have these two stars, they are of the same mass, center of mass will be in the middle. If one is more massive than the other, center of mass shifts towards the heavier body. Now, sun is much more massive than the planets, so center of mass is within the sun. Now, center of mass moves in the same way as the mass particles, that is the body constituted of the particles move. So, this is the momentum of the center of mass. This is simply equal to the sum of the momenta of all the particles which constitute the body. Similarly, the force equation remains same. Radius of gyration is defined as the distance from the axis of rotation, at which if whole mass of the body were supposed to be concentrated, moment of inertia would be same as with the actual distribution of mass of the body. You take any body, then there will always be a point inside the body where if you suppose that whole mass of the body is concentrated there, then moment of inertia will be same as due to actual distribution. So, if you consider a body of total mass m, and let us say this body is made up of n particles, if k is the radius of gyration, you will say moment of inertia is m k square. Now, suppose this body has n particles and these particles of masses m1, m2, m3 etc., and their distances from axis of rotation are r1, r2, r3 etc., then moment of inertia will say it is the sum of products of masses and the squares of the distances. This is the definition that we have learned today, m1 into r1 square plus m2 into r2 square and so on. Now, if for example, we consider that all these point masses are of the same mass m, then you can write it like this, m r1 square plus m r2 square and so on. You equate the two, I is m k square, m into r1 square plus r2 square plus rn square by n, you get k equal to r1 square plus r2 square plus so on plus rn square divided by n square root. So, it is what? What is this? This is the mean of the square of the distances, and then you have taken the square root. So, you can also define radius of gyration as the root mean square distance of the constituent particles from the given axis. Now, let us study about the two theorems, one called parallel axis and the other called theorem of perpendicular axis. Moment of inertia about a body about any axis is equal to sum of its moment of inertia about a parallel axis through its center of gravity and the product of the mass of the body and square of the distance between the two axes. Now, what does this theorem state? Basically, if you know the moment of inertia through the center of mass, you can calculate the moment of inertia through any axis which is parallel to this axis, that is axis through the center of mass. So, parallel axis theorem gives the moment of inertia about any axis parallel to an axis that goes through the center of mass. So, simply it is equal to moment of inertia through the center of mass plus total mass of the body multiplied by square of the distance from the center of mass of the axis where you want to find out the moment of inertia. Now, here it is very clear, this is the moment of inertia through the center of mass. Say you want to find out moment of inertia through this. Distance between the two is d. You know the moment of inertia through the center of mass. Then to this moment of inertia you add the product of total mass of the body and the square of the distance from this axis of rotation, that is I. So, here if you take a point P, let us say, where you want to find out the moment of inertia, O is a point where you can say that whole mass of the body is concentrated, that is center of mass, that is written as Cm. So, you know moment of inertia through this, you want to find out moment of inertia through this point P. Let us say P point has coordinates A and B. Say you have a mass mi here. Now, the distance from the pole of y axis of this mass is y I minus b, and along the x axis it is x I minus a. So, what you will do is that you will simply sum up the moment of inertia along the x axis and that along the y axis. So, ICM is mi into xi square plus yi square. So, moment of inertia through the point P will be mi xi minus a square yi minus b square. Now, these expressions do not involve the coordinate zi measured perpendicular slices. Let us extend the sums to include all particles in all slices, and then this is the moment of inertia through the center of mass. A square plus b square is simply equal to d square, gives you md square. Perpendicular axis theorem states that if you know the moment of inertia of a body of a lamina along the x axis and the y axis, you can find out the moment of inertia along the z axis. अगर सानू x axis करनी moment of inertia पता है और y axis करनी भी पता है, तो जो axis perpendicular है इस lamina दे उधर moment of inertia कितना होएगा, it will be equal to sum of the moment of inertia along these two mutually perpendicular axes. So, moment of inertia of a plane laminar body about an axis perpendicular to the plane is equal to the sum of moments of inertia about two mutually perpendicular axes in the plane of the lamina, such that these three axes have a common point of intersection. This is valid, this theorem is valid only for flat objects. This is the derivation of this theorem, we will not go into the detail now. Now, moment of inertia of a rod. You can consider a rod made up of small masses, the total mass being capital M and the total length of the rod being capital L. Then mass per unit length is m by L. So, this is the rod here, the total mass is m. Now, how do we calculate moment of inertia here? You consider a small mass dm here at a distance r from this axis through the center. Then I is equal to mass dm, moment of inertia we defined as product of mass into square of the distance. So, this small mass dm that has been taken multiplied by square of the distance integrated from initial value of 0 to total mass m, or else you can go in for this, that dm is m by L into dr, this point is minus L by 2, this point is plus L by 2, and you will get the final result to be 1 over 12 into ml square after integrating r square dr, which gives you r cube by 3. If you want to find out moment of inertia about one end, so here you use the theorem of parallel axis. Center of mass जो थानू पता लग गया moment of inertia, which is 1 over 12 into ml square. You want to find out moment of inertia through one end. Now, this distance is L by 2. So, it is equal to moment of inertia through the center of mass plus m into distance square. M into distance is L by 2 square means L square by 4 gives you 1 by 3 ml square. Similarly, you can find out moment of inertia of a ring, which will come out to be mr square, and through the diameter it is half mr square. You do not have to go into these details. When a body rotates, it has got two kinds of energies. One is called rotational kinetic energy and the other is called translational kinetic energy. जो बॉडी रोटेट कर दी है अपनी एक्सिस पे, तो रोटेशन करके भी उसको एनर्जी है, ट्रांसलेशनल मोशन करके भी उसको एनर्जी है. टोटल एनर्जी इज रोटेशनल किनेटिक एनर्जी प्लस ट्रांसलेशनल किनेटिक एनर्जी. Now, if you make these things move over this inclined plane, all these objects have same potential energy, same height तो सिटे गए, same mass है, but the time it takes for them to get down the incline depends on how much moment of inertia they have. जिन्ना ज़्यादा moment of inertia होएगा उन्ना हौली आएगा, जिन्ना moment of inertia घट होएगा उन्ना ज़्यादा जल्दी आएगा. So, here the moment of inertia 2 by 5 mr square है, so it will come down first. Now, different moment of inertia of different bodies This is a rod here, moment of inertia is 1 over 12 ml square. Moment of inertia of a hollow cylinder is half m r1 square plus r2 square. For a solid cylinder it is half m r square. For a thin walled hollow cylinder it is m r square. For a solid sphere it is 2 by 5 m r square. For a hollow sphere it is 2 by 3 m r square. This is another slide which shows the moment of inertia of different bodies. So, what we have studied today is equations for rotational motion with constant angular acceleration have same form as the equations for linear motion with constant acceleration. Another thing that we studied was that the rotational inertia depends not only on the mass of the object, but it also depends upon how the mass is distributed around the axis of rotation. An object which rotates has both rotational as well as translational kinetic energy. So, if it is translating as well, then you have to add both translational and rotational kinetic energy. Thank you.